Okay, so let's actually take a function and find the vertical asymptotes. We'll shift this up. Sort of have prepped an example function, right? So the visuals we're going to end up with will be something like this. We're not quite going to get enough information to actually really know sort of positive infinity versus negative infinity. We'll do that once we actually make our sketches at the very end. But let's try to find some vertical asymptotes. So I've made a pretty simple rational function. So we've got just a nice x plus 3 up top and an x squared minus 16 on the bottom. So this is our sort of p of x on top and our q of x on the bottom. So we have sort of numerator and denominator polynomials. I'm going to tie in finding the x-intercepts to this. They kind of are going to go hand in hand in our strategy. This is sort of steps 3 and 4. They're kind of linked. In theory, you can do them separate, but it's tough to kind of do one without at least acknowledging the other. And so what this is going to amount to is, so factor the top and the bottom. Set them equal to 0. And then solve for our x's. This is sort of on purpose a pretty nice value, so we're going to do sort of x plus 3 equals 0. We'll solve for that x, and we'll do x squared minus 16 equals 0, and we'll solve for that x. So the x-intercepts are coming from the top. So that's for us x plus 3 equals 0. That's really fast, right? That's just going to amount to subtracting the 3 over, and we're just going to get x equals negative 3. We'll mark that for now. We should technically check it into the bottom, or at least see what the values are that will give us a 0 in the bottom before we kind of officially declare that that's going to be an x-intercept. This again is kind of why these things go together. Our potential vertical asymptotes from the denominator, so that for us is going to be x squared minus 16 equals 0. This is a quick factoring, right? This is our sort of difference of squares. I'm sort of on purpose going to be giving us sort of nice things to factor. Obviously you can do this with longer, more complicated factoring things, but I'm going to try to keep the factoring here short, so we can focus more on the concepts and less on having to deal with a bunch of ABC type stuff. So that's going to be our difference of squares. So that's going to be sort of an x plus 4 and an x minus 4. And so we can see pretty quickly, right, that's going to give us two different values, x equals negative 4 and x equals positive 4. And so the thing here that's important that we need to sort of consider is, do any of these two values from the top and the bottom overlap? We can see sort of obviously that they don't, right? Negative 3 versus 4 and negative 4, all of them are different numbers. There's no overlap between those values. And so what that means then is x minus 3 for us will be an x-intercept, right? Because the bottom is not 0 at x equals 3, so as long as that, sorry, x equals negative 3, let's sneak that negative in there. And then if we look at the bottom, negative 4 and positive 4, so we'll have vertical asymptotes at x equals negative 4 and 4, since the top is not equal to 0 at either of those coordinates. So you're doing kind of a reference thing. You're sort of taking the bottom and the top values, the different x values you get when you set them equal to 0, and just sort of checking them against each other. Let me show you an example where we do have some overlap and like what would happen. Shift to a new page. Pardon my hand stuff. So same thing, let's find the vertical asymptotes. So let's do h of x. I'm going to do pretty similar function. What did we just have? X plus 3 over x squared minus 16. I'm going to sort of set us up where instead of x squared minus 16, let's do x squared minus 9. So I'm kind of on purpose setting us up so that when we factor, in some sense we could almost do that right from the beginning. If we sort of factor both the top and the bottom, we're going to see pretty quickly that there's overlap, right? So in some sense this is obviously just x plus 3. But if I factor the bottom, right, so this x squared minus 9, that's our difference of squares, so that's going to be an x minus 3 times an x plus 3. So what that means is as I set these equal to 0, right, from the bottom I'm going to get x equals negative 3 and 3. And then from the top, I'm going to get x equals negative 3. So there is some overlap, right? This minus 3. There is some overlap there. What that means is that's not going to be, for us, an x-intercept or a vertical asymptote. That means we're going to have sort of a gap or a hole at x equals minus 3. I can do, just to sort of check the box, x equals 3 is going to be a vertical asymptote, right? Because that doesn't exist up top. And so what's going to happen here for this like gapped value, the sort of implication here is if we have something that makes both the top and the bottom 0, well, it must be the case that so if the top and the bottom are both equal to 0, what that means in some sense is that there must be an individual like polynomial piece that they have in common, and so you can kind of anticipate what it's going to be. In this case, if we have negative 3 as a value that makes both the top and the bottom 0, that kind of implies that x plus 3, right, would be the term that gives us a 0 and that both the top and the bottom have it. So my kind of factored version, right, is this x plus 3 on top, and then it's this x minus 3 times x plus 3. And so you can see, right, the x plus 3 is a term that they both share. So what we're going to do here is we're going to simplify and cancel our sort of like problem slash like common term, right, this sort of common part, the overlap. So in some sense this becomes just 1 over x minus 3. Now the catch here is that's not the same as the actual original function. The original function has both of those things, and so if I do try to put a negative 3 into the original, it's going to make the denominator 0 and give me an undefined value. So like technically, right, h of negative 3 is undefined. And what we're going to do is just, if we do this like simplification and cancel out, it's not going to give us an actual number here to sort of plug in and graph, but it is going to tell us where the hole exists, and we can plot that hole as an open circle. So what we're going to do is if I take x equals negative 3 right into this simplified version, 1 over x minus 3, so that's going to become, right, 1 over negative 3 minus 3. So that's going to become a 1 over negative 6, aka negative 1/6. So I'm going to get an open circle, right, a hole at the coordinate. So x is negative 3 and the y value is negative 1/6. So I'd have some sort of graph where maybe part of it, oh, whoops, I'm sorry, I'm off the page. So I'd have some sort of graph, right, where I'd have this coordinate, -3, -1/6. I've got sort of a line and a function and a graph going to the left and the right above it. Obviously, you're still going to do all this other behavior and sort of graph all these other pieces. But instead of getting a full asymptote and having this like catastrophic sort of failure happen where everything shoots off to space, all we do is we just have this one little point that's sort of just like plucked out. So we'll show that with an open circle, and the rest of it will sort of graph according to the normal patterns. I'll sort of just tell you right off the top, that doesn't happen tons and tons. It doesn't happen tons and tons in the homework. It probably won't happen tons and tons in our examples. Finding the asymptotes and graphing those is going to be a little bit of a higher priority for us, but it is something that can happen, and so something you need to watch out for.